Ice charts, not frozen water, LOL. All right, so ice charts allow us to estimate the amount of each substance once the reaction reaches equilibrium. So an interesting thing here is we don't necessarily, in these kind of problems, go from just A to making B. When we did stoichiometry and limiting reagent and all that kind of stuff way back when, we did that. So we knew if we had a certain amount of A, we would make a certain amount of B. But because these reactions reach equilibrium, just because you have some of A doesn't mean it's all going to turn into B. But using this ice chart, you'll be able to figure out about how much you would end up with for all of them. We can only use ice charts when our substances are in the gas or aqueous forms, so we can't use it for solids or liquids. All right, so all the problems are going to probably have gases or aqueous in there, and we'll do something special with some solids later on. I'll show you how to do that, but all right, let's keep on rolling. So what does ICE stand for? It stands for initial is I, initial concentration. C stands for the change in the concentration, and then we'll jump and then come back. E stands for the equilibrium concentration. All right, so those are the three things that ICE stands for: I, C, and E. Okay, so let's talk about what these mean. So the initial concentration, it says this is the initial concentration of the reactants and the products. Since this is the beginning of the reaction, the concentration of the products is 0 because the reaction hasn't started yet. So this is just how much reactants you're starting with. That's it for the initial. This is usually given to you in a problem, but we could solve for it as well. The change in concentration, this is the change in the concentration. The reactants are starting to be used up, so the reactants decrease, and the products are starting to be formed, so the products will increase. So that makes sense, right? Just from like a chemical point of view, we're starting with no products, and then we're going to make some products, and we're going to use up some reactants. All right, cool. The equilibrium concentration is after the system reaches equilibrium, there will be some products and some reactants all existing together. So that's going to be, all right, so once it reaches equilibrium, how much of each do we have? And that's going to be our kind of like our goal, is figuring out that, the equilibrium concentration. Once equilibrium is reached, the reaction doesn't stop. It continues, but every time one reactant is changed into a product, one product is changed back into a reactant. And this is the meaning of equilibrium, and this just keeps on going forever. So that's why if you see the A, and then B, and the 2 arrows, if A gets turned into B once, B gets turned into A. They just keep on going at the same time. Which is also why they say the reaction doesn't stop, because it's still doing that. It's still going from A to B and B to A, but it's an equal amounts. So if you have 5 A's that go to B's, you have 5 B's that go back to A. That's equilibrium, okay? All right, so setting up an ice chart. So for this, I picked a very simple equation. It just has one reactant and then one product, okay? So just to keep it real simple, that's our equation. Even though it doesn't look like an equation, it's just this turning into this and going back and forth. They also gave us some information. They gave us what K equals, and they told us that we have 1 molar concentration of N2O4, all right? N2O4 is our reactant. So what they're doing is they're telling us this is how much of this we have in the beginning. Now an ice chart is literally a chart. There goes Mr. House. So we need to set this up like a chart. And then we'll fill in some stuff. So it's kind of like a big box. And you can wait to fill it in until you see what I'm going to put in there. But it'll kind of look like this chart here. And because we have 1 molar of N2O4, we actually write that here. All right, that's how much we started with. How much of this product do we start with? Before the reaction, yeah, we start out with 0, right? We don't have any product. All right, so the initial of the ice chart is we have 1.0 molar of this reactant, because it told us, and then we don't have any product. We won't have any product usually when we start these things, okay? So just to keep it simple. Now the change is, how much does it change? Now, by looking at this, we're not sure how much it changes by, right? So we can actually make a variable for this. So give me a variable. What do they always use in math? X. All right, so it's going to be X, but is it going to be a positive X or a negative X? We can determine that. Meaning, are you going to end up with more reactants or less reactants when the reaction starts? More or less? Less, right? They're going to be used up. We're going to use up some of these reactants to make the products. So this is going to be a negative X in here. All right, everybody cool so far? All right. Every time we use up one of these, all right, it's going to be negative X. Now, how much product are we going to make? Well, we don't know the number, right? So we're going to use the same variable. Are we going to be making more of this? Yeah, we don't have any, so we're going to make product. But it's not just going to be X, it's going to be 2X. Because every time you use one of these, you'll get two of these. So this is going to be plus 2X. All right, so we get the coefficient to be that 2 there. And then the change in equilibrium is just combining your I and your C together. And since it's a variable, you don't have to really do any math. You just put 1.0 minus X, because you're combining I and C together. So it's 1.0 minus X. And then you have 0 plus 2X. That's just going to be 2X. And that's filling out your ice chart. All right? So you're just kind of, you can think of this as adding them together. All right, so 0 plus 2X gives us 2X. 1.0 molar minus X gives us 1.0 minus X, because we don't know what X is, right? Okay, any questions with that part of the ice chart? With the ice chart, no? Okay, cool. Okay, the next thing that we can do is we can actually set up the K expression. So in this chapter, you're gonna have to do two things for every problem. Usually you'll set up an ice chart, and then you'll also have to figure out what the K equals, all right? Now, it tells us that K equals 0.1, but check this out. If we know the 0.1 and we have X's, we can use that 0.1 to solve for X, all right? Now, we're not gonna solve for X in this one, but we're gonna set it up, all right? So what goes on the top, what goes on the bottom? As far as the equation goes, do you remember what always goes on top for any equation? What is it? Yeah, it's the products over the reactants. Okay, we're not going to put numbers in yet, but what's the product? What's the formula for the product? It's going to be that 2NO2, right? So we put the NO2. What do we do with that 2 though? What do we do that with that coefficient? Did it yesterday. The coefficient becomes the exponent. Good. So we move it up there, right? The coefficient becomes the exponent. Good. That's where I'm getting this from. And then the reactant goes on the bottom. Okay. Now we're going to plug in all of our variables and all of our numbers. So we set up the K equation. We now have it with kind of like the equation in there, but now we're going to substitute. So 0.1 equals, all right, instead of saying NO2, we go to our ice chart and we look at it and we would say, oh, NO2 is actually 2x, the quantity squared. I know it's getting a little heavy, but 2x is from here, it's from the chart. The 2 is just from here. And then the bottom one is just 1.0 minus x, like that. All right. Okay. Any questions with that? It's weird. Now, I know I said let's not solve for x, but I'm going to break my own rule because why not? All right? You guys feel comfortable with this, maybe? So we can do some more stuff. Let's use our algebra, all right? This is squared, right? 2x quantity squared. So what's that actually going to become once you do all that fancy squaring? What do you think? You have to distribute it, right? So it's going to become, what's 2 squared? 4x squared, right? Because you have to distribute it out. So now it's 4x squared over, now, here's the problem. If we left it like this, how would you solve this in Algebra 2? What equation would you have to use to solve this? Or what would you have to do for this? There's something you have to use to solve these kind of problems. Unfortunately, yeah, you would cross multiply, but there's something a little bit more in there because you have the x and you have the x squared in there. Anybody know? Quadratic equation. You guys learn about that? Where you have like an x and an x squared and you have to use all this crazy stuff to solve for this. So what we do in chemistry to make it easier, because some people haven't gotten there in math, and honestly, I don't want to deal with this, is we actually, whenever you have like 1.0 minus x and it's equilibrium, if you think about it, this is kind of a big number. I know it's 1, but x could be like 0.0005. It could be something times 10 to the negative 5th. It could be a really small number, right? And if you take 1 and subtract a very small number from it, and then round for sig figs, it might still be 1, which is weird, but because this number is so tiny, it's insignificant. So in honors chemistry, what we're gonna do is we're gonna drop it. We're literally gonna get rid of it. It's one of the greatest things about this class is you're just gonna say, I see you, but I'm gonna drop it. Because it might be small enough where sig figs don't matter. Now in AP chemistry, Miss Blake will tell you all about how to do it if you take that class and how to solve for it and all that stuff, which is great. But for this year, we're not gonna do it, all right, which is totally allowed. I'm not breaking any rules. Well, I might be, but that's okay. So if we get rid of that x now check out how that changes this problem. This is 1 on the bottom, right? So it's like it's not even there. So this problem actually now just becomes 0.1 equals 4x squared, right? And you can solve this one. What would we divide on each side first? What are we going to divide on each side to get x by itself? Yeah, we're going to divide by 4 on each side. All right, and that's going to give us 0.1 divided by 4, 0.025, I think. So now we have 0.025 equals x squared. How do we get rid of that x squared? What do we do to it? Yeah, exactly. We square root it. And that's going to give us x equals the square root of 0.025, which I have 0.16. Some of you guys can back that up if you'd like. Make sure that that's good. Sig fig wise, k is a constant, so we ignore that for sig figs, but 1.0, 2 sig figs, probably close enough for us. So now we have x, even though it said do not solve for x. Now you're like, well, all right, what's the point of this? What does x even mean? Well, if you go back to this problem, what this tells us now is how much of this stuff we have at the end. For example, we started with 1.0 of this. Now minus x is how much we used up, right, from the ice chart. So that means 1.0 minus 0.16 equals how much we have at the end of this. You see how that's a tiny number? Now it's not extremely small, but that's okay. It's 0.84. So we'll have 0.84 molar of this at the end of the reaction. That's kind of our E. And then for this one, what we have is we have 2x. So we have 0.16 times 2. So we'll end up with 0.32 molar of this at the end of the reaction. So it's kind of like, oh, that's the whole point of this, right? It's to figure out how much of this stuff we have at the end. So if you look at this, we have more reactants at the end of this problem than products, because we have 0.84 of the reactants. We only have 0.32 of the products, which makes sense because K was 0.1, and K is smaller than 1. That means that we'll end up having more reactants than products. If K was larger than 1, we would expect us to have more products than reactants. All right? Okay. Now, that was the first time we went through a problem like this. We're going to go through many problems, all right? And you're going to get the feel of it. But overall, that's kind of the idea with this. Okay, does anybody have any questions? Yeah, Julie.
So is it always going to be set up like 0.1 equals 4x2? Like that's set up, like you drop the negative x?
Yeah, if you ever have, that's a great question. If you ever have anything, because this could have been a 4 minus x. Whenever you have something minus x on the bottom, you're always going to do this dropping.
Okay.
You're always going to drop it, yeah.
So it's always going to be set up like that? Like nothing like weird?
Yeah, sort of. Yeah, and we'll go through all the weird ones too. But yeah, this is a very basic version of it. And like, as far as like what I want you guys to get out of this today is, could you set up another ice chart? Yeah, you could plug all the numbers in. You saw where they came from. Could you set up the K equation? Yeah, definitely. We actually did that yesterday. All right. And then once we get into this is kind of the stuff that's going to take us much longer to feel real comfortable with. But it's just algebra, we're just going to follow the same rules for everything. All right.